Ladies and gentlemen, welcome. Senhoras e senhores, bom dia. A Universidade Federal de Minas Gerais tem a honra de recebê-los para mais um dia do UFMG Seminar Series Intelligence and Artificial Intelligence. É uma realização IEAT, Instituto de Estudos Avançados Transdisciplinares da UFMG, patrocínio CGI.br, NIC.br, Comitê Gestor de Internet no Brasil, Confeia, Conselho Federal de Engenharia e Agronomia, Eletrobras, Embaixada dos Estados Unidos no Brasil, Vetor Editora, Embaixada da França no Brasil, Dadosfera e Fundep, Fundação de Desenvolvimento da Pesquisa. Nós vamos dar início, então, senhoras e senhores, à programação. E agora, já presentes conosco nesse evento híbrido, o tema Foundations and Ethical Aspects of Artificial Intelligence and Cognitive Science. Teremos a participação do professor Jack Copeland, professor Oron Chagrir, professor Robert Altman, professor Zhao Fan e, como mediador, o professor Reni Ierria. Reni Ierria, full professor at the Electronic Engineering Department of UFMG, with bachelor's and master's at ITA and PhD in Electric Engineering at the Niagara University. Nós lembramos que teremos um café às 10h30 da manhã. Senhoras e senhores, então, para conduzir os nossos trabalhos, com a palavra, professor Reni Ierria. Bom dia, Reni.
Good morning.
Good morning, Reni.
So we can start now. I have to thank, first of all of our guests, Professor Jack Copeland, who is a professor of philosophy at the University of Canterbury in New Zealand, Professor Zhao Fan, who is at the JSPS International Research Fellow at Kobe University in Japan, Professor Oron Chagrir, philosopher and Schumann Chair of Philosophy and Cognitive Science at the Hebrew University in Jerusalem, and Professor Robert Altman, professor at the Center of the Study of Rationality in the Hebrew University of Jerusalem and Nobel Memorial Prize in Economic Sciences in 2005. So Jack will start his presentation together with Zhao Fan. And so Jack Copeland, so I thank you very much for being here. You can start your presentation anytime you wish. If after the presentation, we will have specific questions about your talk. And at the end of the meeting, we will have a general discussion. I understand that it's 1 o'clock in the morning for you, so it's okay if you leave that at any time. But you can start now, and I'll be here for anything you need. Thank you very much.
Okay, thank you. Let's hope this screen share works. So, welcome to the talk. I hope you're going to enjoy it. On my way of looking at things, Turing's Second World War enigma-cracking bomb at Bletchley Park was the first milestone on the road to modern AI, or machine intelligence, as Turing called it. The bomb used mechanized heuristics to narrow the search space. At Bletchley Park, Turing circulated a typescript concerning machine intelligence. Now lost, this was undoubtedly the earliest paper in the field of AI. The myth you read in the textbooks that the field was born in 1956 at the Dartmouth Summer Research Project on Artificial Intelligence, organized by John McCarthy and Claude Shannon, gets the time of origin of the field incorrect by more than a decade. In 1947, Turing gave us what was, so far as is known, the first public lecture on AI by a practitioner. He told his dumbstruck audience, "I feel that one is obliged to regard the machine as showing intelligence. What we want is a machine that can learn from experience. The machine must be allowed to have contact with human beings in order that it may adapt itself to their standards." The following year, Turing wrote AI's first manifesto entitled Intelligent Machinery. He hypothesized that, quote, "intellectual activity consists mainly of various kinds of search," unquote, so prefiguring Newell and Simon's heuristic search hypothesis, which came along in the following decade. Turing's manifesto also brilliantly introduced a raft of core concepts that were subsequently reinvented by others, including the idea of a genetic algorithm and proposals for achieving AI by means of trainable networks of model neurons, an approach we all know now as connectionism and deep learning. For good measure, he gave us the Turing test and also pioneered chess programming. And prior to that, in 1936, in pre-war Cambridge, Turing also gave us the fundamental logical principles of the modern computer. It's these fundamental principles and their history that Zhao and I are going to focus on today. The fundamental principles on which the machines we use to do AI are based. We're going to take you on a deep dive into the history of computers. Not everyone, though, sees Turing in the glowing way I've just presented. Zhao and I are also going to examine the strange phenomenon of Turing denial. As I've just explained, Turing played a fundamental role in the development of the modern computer. However, he was a misunderstood and relatively isolated figure, and he made little attempt to communicate with the main centers of post-war computer development in the US. In histories of the computer that were written in the 20th and early 21st centuries, Turing often received at best a minor mention, or even no mention at all. For example, the following crashing non-mention is from a famous computer science textbook of the 1970s. Bell and Newell. They said, the early story has often been told, starting with Babbage and early mechanical calculators, through Hollerith punched cards, on to the relay calculators at Bell Laboratories and Harvard, up to the birth of electronic machines with ENIAC, and finally to the stored program concept with the von Neumann machine at the Institute for Advanced Studies, EDSAC at Cambridge University, and EDVAC at the University of Pennsylvania, with the contemporary developments by Zuse in Germany often left out. They did manage to mention the sadly neglected German pioneer of computing, Konrad Zuse, but not Turing. All that changed in 2012, Turing's centenary year, and he's now popularly regarded as the founding father of computer science. But an academic backlash is occurring. Turing deniers, as Zhao and I call them, seek to show that, in fact, Turing made no very significant contribution at all to the development of computers and computing. There's an older tradition of Turing denial too, which we'll also be looking at. But before examining this strange phenomenon of Turing denial, I'll take a quick look back at Turing's famous 1936 paper on computable numbers. And just as we leave this wonderful image, I should thank the artist Debbie Zenith for allowing me to use it. She got the blue eyes really well, I think. Of the many important innovations that this paper contained, I want to highlight two. First, there was the idea of controlling a computing machine by storing editable coded instructions in the machine's memory. This is the logical heart of the so-called stored program concept. Second, there was the idea of a universal computing machine, an all-purpose machine so flexible that it can be programmed to carry out the work of any and every special-purpose computing machine. Nowadays, we can all easily reel off a long list of the jobs that the universal machine is capable of doing: numerical calculation, word processing, playing chess, photo editing, translating German into English, and so on and so on. It seems almost an understatement to say that these two ideas are of fundamental importance in computer science. However, this man, John von Neumann, is so often described as the originator of the stored program concept, not Turing. How did this come about? Von Neumann made the stored program idea very well known in high-profile lectures and written publications, and his logical contributions to bringing about the implementation of the idea in real hardware were pivotal. I don't think von Neumann himself cared terribly much about matters of credit. For him, it was the ideas that mattered, not where they came from. He certainly never claimed the idea of the stored program universal machine as his own. And when he did show a mild interest in assigning credit, he tended to give credit to Turing. Here he is saying that Turing's great positive contribution was to show that one definite mechanism can be universal. That was in 1946. And then 3 years later, in 1949, he said, the importance of Turing's research is just this, that if you construct an automaton right, then an automaton of this complexity can, when given suitable instructions, do anything that can be done by automata at all. So that's giving credit fair and square. But nevertheless, one could hope to find something even more specific in von Neumann's Nachlass. He doesn't specifically mention electronic computers in the statements I just quoted. It would be good to find him naming Turing actually in the course of a discussion about the fundamental principles of building an electronic computer. This missing link, this elusive missing link, if found, would be a significant addition to our picture of the past. That's a plot point, of course, and we'll be returning later to this topic of the missing link. But next, on to the Turing denier. My first example is George Davis, an early Turing denier in the UK. Here he is working on the Deuce computer. The Deuce was effectively Turing's computer. In his 1945 design document, Proposed Electronic Calculator, Turing set out the design for his ACE, or automatic computing engine. The engineers built a smallish pilot version called the Pilot ACE, which was immediately recognized as being such a powerful computer that the English Electric Company started manufacturing Pilot ACEs and marketing them under the name Deuce. The Deuce was a major workhorse during the first decades of the computer revolution, and there were Deuce installations all over Europe. Davis was a biggish wheel in the English Electric Deuce operation. He didn't think much of Turing. For whatever reason, he spent his life strenuously denying that Turing's pre-war work had any connection with post-war computer developments. He said that the universal Turing machine was a purely abstract mathematical notion, and there was no connection, even in Turing's mind, between it and the stored program electronic computer. Back in the 1990s, Davis said to me very forcefully, look, Turing didn't even mention uncomputable numbers and the Turing machine in his document Proposed Electronic Calculator. You can see Davis's point. If it were the case that Turing set out after the war to build a universal Turing machine in electronic hardware, then surely he would have mentioned uncomputable numbers in Proposed Electronic Calculator. But as Davis gleefully insisted, he didn't. I took that as a challenge. As you would expect with such a complex document, Proposed Electronic Calculator went through a number of drafts, none of which has survived, or so it seems. But to my great delight, I managed to track down a very few pages of one of the drafts. And by considerable good fortune, one of those pages did mention uncomputable numbers and the Turing machine, so establishing that George Davis and others who've argued in the same way are wrong. This is what Turing wrote in his draft, one of his drafts of Proposed Electronic Calculator. In computable numbers, it was assumed that all the stored material was arranged linearly, so that in effect, the accessibility time was directly proportional to the amount of material stored. This was the essential reason why the arrangement in computable numbers could not be taken over as it stood to give a practical form of machine. So there it is from Turing's own typewriter, replete with his usual thicket of typos. Back in those days, in the 1940s and through into the 1950s, Turing denial, or even Turing ignorance, was certainly far from being the default. To many of those in the know, the connections between uncomputable numbers and the new developments in electronic computing were plain. Let me give you some examples. This is Donald Mickey, who worked with Turing as a code breaker at Bletchley Park and who subsequently pioneered artificial intelligence research in the UK. Mickey was closely involved with the Bletchley Park Colossus. This machine was designed by Tom Flowers, and the Colossi were the earliest large-scale electronic computers. The first was installed at Bletchley Park in January 1944. Colossus wasn't stored program, and it was far from being universal, very far. But nevertheless, the computer's racks of high-speed digital electronics pointed the way to a universal Turing machine in electronic hardware. Mickey said, "In the numinary, we were fully aware of the prospects for implementing physical embodiments of the universal Turing machine using vacuum tube technology." The numinary was the section at Bletchley Park where the Colossi were housed and operated. It was run by Max Newman, the Cambridge mathematician who'd helped Turing to ready uncomputable numbers for publication in 1936. The period Mickey is talking about here is a year or more before von Neumann wrote his famous 1945 report, setting out his own plan for an electronic stored program all-purpose computer. Next example, Sir Charles Darwin, grandson of the great Charles Darwin and director of the National Physical Laboratory in London. Here he is writing in a memo to the British government's Department of Science and Industry, automatic computing engine. This is a proposal to construct a computing machine of very much greater potentialities than anything done hitherto. The possibility of the new machine started from a paper by Dr. A.M. Turing some years ago. The principles he, Turing, enunciated have now become practicable since it is possible to use electronics in the machine. We even have a completely explicit statement from Turing himself on the connection between uncomputable numbers and post-war computing developments. This is in 1947. Some years ago, I was researching on what Some years ago, I was researching on what might now be described as an investigation of the theoretical possibilities and limitations of digital computing machines. I considered a type of machine which had a central mechanism and an infinite memory which was contained on an infinite tape. Digital computing machines are in fact practical versions of the universal machine. There is a certain central pool of electronic equipment and a large memory, and the appropriate instructions for the computing process involved are stored in the memory. But despite statements like these from people who knew the facts, Turing denial has become a powerful motif in computer history, as Zhao will describe. Over to you, Zhao.
Thanks, Jack. A typical objection from Turing deniers concerns whether the stored program concept is originated from uncomputable numbers. They argue that this concept has its own roots, which predate Turing's 1936 paper. For example, Vardy contends that the stored program concept can be traced back to Gödel's 1931 paper on incompleteness. Vardy said here, the claims that Turing invented the stored program computer, which typically refers to the uniform handling of programs and data, are simply ahistorical. One can trace the canon of the idea of handling programs and data uniformly back to Gödel's arithmetization of provability in 1931. The idea then showed up again in the lambda calculus, recursive functions, and Turing machines. A second typical objection from Turing-Deniers concerns whether the Turing machine concept is purely mathematical. Wilkes, designer of the EDSA computer at Cambridge University and a Turing Award winner, asserted that the Turing machine was a purely theoretical concept and was used to prove an important theorem in mathematical logic. There's no hint in the paper that the Turing machine might have any connection with practical computing machinery. He repeated this view in an interview in 2009, saying there was no distinction in that paper on computable numbers that had any practical significance. Similarly, Burks, who was involved in the design of several pioneer electronic computers, ENIAC, EDIAC, and the Princeton computer. Burks cited Alan Turing's concept of a computing machine described in his 1936-7 paper was not only outside that causal chain, the chain that Burks was talking about is from the special purpose Atmos for Barry computer to the general purpose ENIAC and on to the stored program EDIAC and IAR's computer. But it was a purely theoretical design, not directly applicable to the design of any practical computer of any technology. A third objection from Turing-Deniers concerns whether Turing's 1936 paper had any significant impact on the development of the modern computer. For example, artificial intelligence pioneer and Turing Award winner McCarthy said the term computer now designates a universal machine capable of carrying out any arbitrary calculation, as propounded by Turing in 1936. The possibility of such a machine was apparently guessed by Babbage. Curiously, it does not seem that the work of either Turing or Babbage played any direct role in the labors of the man who made the computer a reality. Historian of computing Campbell Kelly proposed a counterfactual argument, saying, posing the counterfactual, would the computer have developed more slowly or much differently had Turing not lived? Most computer historians, except some in Britain, believe not, and for this reason, he does not feature significantly in most histories of computing. In this regard, Turing can be seen as somewhat like Babbage, a monumental figure that has profoundly affected our historical perspectives on computing, but had relatively little influence on its practical development. Some Turing-Deniers question the claim that Turing's 1936 paper played a significant role in the development of the modern computer by claiming that it is only a posteriori reconstruction. For instance, Daylight cited, computer scientists in the 21st century have the tendency to construct a set of foundations for computer science in which ideas and events that had not been understood as connected when they happened are retrospectively integrated. The connection between universal Turing machines and computers is one notable example. Turing-Denier Corey said, to the extent that earlier stored program computers of the mid-1940s can be seen as physically embodying ideas discussed in the 1936 paper Computable Numbers. This is mostly a result of hindsight and says little about Turing's ideas before the war. Munir Kuhn said, mediating on the vision of the abstract Turing machine, materializing into hot war between 1936 and 1949, a theologian could even understand it as a secular version of the Christian process by which the verb became flesh. To remain in the computing realm, I tend to consider this model as a founding myth of computer science and a posteriori reconstruction more than an accurate historical account. Turing-Deniers Demoux and Boeing, in a paper co-authored with Daylight, said the Turing machine was appropriately a posteriori by computer scientists to serve as the conceptual model of a general-purpose digital computer, and the store program computer is a construction after the fact started off by IBM. Another theme among Turing deniers concerns Turing's influence on von Neumann. This is the first page of a recently rediscovered typescript of 3 lectures by von Neumann. Ironically, this typescript is discovered by a Turing denier, Mark Priestley. Jack will be saying more about this lecture soon. The reason this typescript is so interesting is that it contains what seems likely to be von Neumann's early surviving mention of Turing's universal machine. Based on this typescript, Turing deniers Haig and Priestley published a paper in 2020. The title of their paper is Von Neumann thought Turing's universal machine was simple and neat, but that didn't tell him how to design a computer. According to Haig and Priestley, von Neumann freely acknowledged the contribution of Turing's 1936 paper to his work on automata theory, but made no such connections in his discussion of computer design. Furthermore, Haig and Priestley contend that this document shows that the abstraction from constraints of space and time that eventually made Turing machines so useful for computer scientists looking to lay theoretical foundations for their new field made them irrelevant to people trying to design the first real electronic computers. Jack.
Thanks, Zhao. I'm going to say a little more about Turing denier Thomas Haig. Haig has found a novel way to deny Turing credit for the stored program concept. According to Haig, the term stored program rarely appeared in early documents. This fairly obscure term, he says, originated in an IBM internal memo in 1949. Haig claims the stored program concept is largely a historian's creation. He says, in the late 1970s and 1980s, the idea of the stored program computer was borrowed from technical discourse, developing from a fairly obscure term into a central concept in heated debates over what should be considered the first true computer and why. So the stored program concept is not Turing's invention at all, but a later concoction, he says. However, his claim that the concept was by and large a construction of historians simply does not withstand scrutiny. He's right that the phrase stored program was generally absent from the very early documents. The reason, though, is simply that the founding fathers tended not to use the word program at all. Von Neumann preferred orders, as did Konrad Zuse. Turing continued to use his 1936 term instruction table, or simply instructions. Here is Turing lecturing in 1947 on his own universal computer, the ACE. He said, the machine will incorporate a large memory for the storage of both data and instructions. Sounds like the stored program concept to me. Next, a quote from Freddie Williams and Tom Kilburn's letter to Nature in 1948, announcing the birth of the Manchester computer. Here they are standing in front of their creation. That's Kilburn on the left, Williams on the right. They called their machine simply Baby. Baby was the first recognizably modern computer, the distant ancestor of all our mainframes, laptops, tablets, and phones. They wrote, the program can be changed without any circuit changes. The essential parts of such a machine are first, a store for information and orders. The pioneering selection they're making here of the terms store and program proved to be a way of speaking that many others would also find natural. Last example. Here is Willis Ware, who was one of von Neumann's team of computer engineers at Princeton. By the time of this lecture, reviewing the development of the electronic computer in the US, usage was sufficiently settled for Ware to say simply what we now know as the stored program machine. Examples similar to these can be multiplied endlessly from books and articles published on both sides of the Atlantic in the 50s and the 60s, long before Hayes' supposed creation of the concept by historians. Let's turn now to von Neumann's recently discovered wartime lectures on high-speed computing, which, as Zhao mentioned, are a key document in the history of computing, since they constitute the earliest known mention of the universal Turing machine in von Neumann's Nachlass. He discussed Turing in the third and last lecture. The first two lectures were about older technology, such as electromagnetic relays and analog computers, and von Neumann dwelled on the greater promise of electronic digital machines. The notes for lecture 3 begin with the title, The Logical Machine of Turing. And in the introductory paragraph, von Neumann made it clear that he was going to focus on the problem of logical control. Then, quoting from the middle of the page, he said, "We shall consider two systems of logic which could be used in building a computing machine. The first, developed by Turing, is essentially a logic machine." Notice the very specific language here. He says, which could be used in building a computing machine. The notes then go on to describe the Turing machine. It consists of two parts, he says, and there's figure 1 depicting the tape and the scanner with its control mechanism. On the next page, von Neumann chatted a bit about Turing machines, and then the concept of the universal machine was described. Quoting from the bottom of the page, "A universal machine is one which can construct any arithmetic function that can be done by a particular Turing machine. Common sense might say that the universal machine is impossible, but Turing proves that it is possible. The idea of a universal machine is simple and neat. To build this machine, one decides on a code to describe each particular Turing machine. Then one puts the definition of each Turing machine on a tape. The new machine reads the definition of a Turing machine and then imitates it." And of course, as von Neumann made clear at the outset of the lecture, he's explaining this idea in the context of a discussion about the problem of logical control, which is to say the question of how to arrange for an electronic machine to perform the desired operations in the desired sequence. Then on the next page, von Neumann jumped to a discussion of pits. Quoting from the top of the page, "A second quasi-logical approach to the problem of computing machines has been suggested by Pitts. He attempts to describe the human nervous system in terms of logic. Pitt, typo of course, thinks of a special relay organ, namely the neuron. His idealized neuron could be imitated by a circuit of vacuum tubes. Hence, we are interested in his developments." Then von Neumann gave an introductory tour of what we now call the McCulloch-Pitts neuron. He introduced the ideas of inputs, output, stimulation, inhibition, two states of the neuron, stimulated or inert, and the idea of a threshold. Then, in the remainder of the lecture, he went on to explain how to construct examples of computational devices out of McCulloch-Pitts neurons, for example, a binary adder and various counting circuits. And there, the lecture ended. One thing the lecture notes don't make clear is why von Neumann juxtaposed a discussion of Turing and a discussion of Pitts. What was the connection supposed to be? No doubt he made this clear to his audience, but we have to figure it out. Von Neumann knew, of course, the McCulloch-Pitts paper of December 1943, with its forbidding title, A Logical Calculus of the Ideas Immanent in Nervous Activity. And he knew that this paper painted a novel and very different picture of Turing machines. In a way, the fundamental topic of that paper was Turing machines, as McCulloch later told. McCulloch said, I started at entirely the wrong angle. And it was not until I saw Turing's paper on computable numbers that I began to get going the right way around, and with Pitt's help, formulated the required logical calculus. What we thought we were doing, and I think we succeeded fairly well, was treating the brain as a Turing machine. In the wake of this paper by Pitts and McCulloch, the control mechanism of a Turing machine could be regarded as being a network of their Boolean neurons. A comment by the mathematical logician Robin Gandy is highly relevant to understanding the connection that von Neumann was making in the lecture. Gandy was Turing's student and friend, and he was with Turing during the last years of the war and during the post-war efforts in the UK to build the first electronic stored program machines. So far as I know, Gandy wasn't familiar with this particular lecture by von Neumann, but here is his account of the relevant connection between McCulloch, Pitts, and Turing. He said, in their seminal 1943, McCulloch and Pitts asserted justifiably that the control mechanism of the universal Turing machine could be simulated by a finite assembly of idealized neurons connected to each other by synapses incorporating delays. Their idealized neurons can be thought of as logical gates and were used in von Neumann 1945 and Turing 1945 as the building blocks for the construction of the executive parts of universal digital computers. Von Neumann's lecture appears to be presenting exactly that Turing-centered recipe for solving the problem of logical control in an electronic machine. The idea he was explaining seems to have been that we can solve the control problem by building something akin to the instruction reading and obeying control mechanism of Turing's universal machine. And we can do that by using McCulloch-Pitts neurons implemented in the form of vacuum tube circuits. So here then is the previously mentioned missing link. And for Turing deniers, the lesson is, at the very least, that in this early lecture on the problem of control in electronic computers, the only names that von Neumann thought he needed to mention were Turing and Pitts. To finish off, it's worth mentioning the somehow instructive fact that Turing denial gets passed on from generation to generation, from teacher to pupil. This is Tom Kilburn, one of the earliest and most influential Turing deniers, who we saw previously with the Manchester Baby. Kilburn hated Turing. For whatever reasons, he systematically denied Turing his rightful place in computer history. Turing denial passes from teacher to student. Here's Kilburn's student, the Turing denier Martin Campbell Kelly. And here is Martin Campbell Kelly's student, the Turing denier Thomas Haig. A dynasty of Turing deniers. It's rather depressing. Okay, that's it. Thank you very much. I can't hear anything. I don't know whether anyone's speaking, but if they are, I've lost sound.
Por acaso o auditório da UFMG está aí? O chair da sessão estaria disponível para falar? Nós não estamos lhe escutando.
No, I mean, Jack and Zal, can you hear me or not?
Yes, yes, I
Yes.
can.
They can hear me. They can hear me. It's muted because if they can hear me. If they can hear me. We are open for questions now. So does anyone have a question? Is it, a gente tem perguntas em algum lugar? Agora. Então, mas aonde estão as perguntas? Tem algumas pessoas que já fizeram? In the audience, is there any questions? Pode presencial. Cadê o microfone? Microfone, por favor. So the microphone is coming for the online audience. Pergunta. O que eu faço aqui agora? Deixa eu ver. Vamos pegar presencial primeiro. Presencial first. Presencial. Alguém tinha perguntado. Somebody asked to here in the audience, no? So how can I? Como é que eu posso ver as perguntas que estão já escritas? Então chama ele lá. Agora. Just a moment. We are now choosing which questions to ask first. Those that were sent in the chat. And so, Oren, you raised your hand.
Yes, I can meanwhile ask a question. Hi, Jack.
Hi,
What
Oron.
is in New Zealand? Yes.
Good to see you.
Yeah, so my question is that, there is in a way something surprising that Turing's, those who deny Turing's contribution to the history of computing are not people who compete with him on the credit. Actually, the people who could compete with him on the credit, like von Neumann and Pitts and McCulloch and people like this, give, as you show, Turing the credit. So how can you explain this disparity in a way?
Well, I think the disparity is only partial. I mean, there are Turing deniers who, contributed themselves hugely to the development of computers. Tom Kilburn, for example, who I spoke about, he was the guy who wired together the first modern computer, the Manchester Baby. And he went on to design computer after computer. He just made enormous contributions to the computer age. But there was this, kind of personal, thing going on between him and Turing. And certainly that's part of the story as to why Kilburn was a Turing denier. I think there's probably more to it than that. I think probably Kilburn and the other engineers in those days saw the danger that their own contributions would be overshadowed by the contributions of the mathematicians, such as von Neumann and such as Turing. Because, the mathematicians were kind of, high-profile figures. Whereas the engineers, with their soldering irons, kind of, who were they? And so Kilburn probably quite rightly sensed the danger that, he would be written out of history. So he kind of did his best to make sure that it was the, him that was remembered and not the mathematicians. And another way that your disparity is only partial. There was also Maurice Wilkes, who Zhao mentioned, who again made very large and distinguished contributions to the development of the computer. I mean, he got the kind of the first usable modern computer working in Cambridge. The Manchester Baby was first, but it was it was a small machine, and you couldn't really do serious mathematical work on it for a year or two. Whereas Wilkes got the Cambridge EdSat going really by just ripping off American designs. but building them more quickly than the Americans managed to. So you can't say that Wilkes was, you know, kind of an insignificant figure.
Thank you very much. I could follow it. Or any, is it enough, or you want to continue?
No, I see that Robert Aumann has a question.
Mm-hmm. So Robert, please. Robert?
Yes.
Okay, go ahead.
I want to add, it wasn't clear to me from the lecture on whose side the lecturer is, whether he's a Turing denier or a Turing fan. Yes, I mean, is it actually true that people who actually developed the computer, the physical computers, were they aware of Turing's paper? Did they use his ideas, or was it sort of independent? And the Turing provides a theoretical background for this, but the practical invention, that it wasn't clear from your lecture on whose side you are.
Well, that's exactly what Joe and I were arguing, that the ideas in Turing's paper were not just circulating amongst theoreticians. They made it into the hands of the people who wired together the first computers, via Turing himself, who spread the word of uncomputable numbers amongst the engineers in the UK, both at Bletchley Park and at the National Physical Laboratory and elsewhere, and also via von Neumann in the United States, who spread the word of uncomputable numbers to the engineers at the Morse School and at Princeton and so on. So yeah, we're opposed very much to Turing denial. I think that's true to say, isn't it, Zhao? That's our claim.
Okay.
Yeah.
Okay, thank you.
I think there are questions in the chat, but I cannot see it here. So I myself would like to ask a simple question, maybe naive, but Jack and Zhao, according to your understanding, the Turing machine is a problem-solving machine that could be somehow programmed, if I can say, to solve the same problem in different ways as it somehow changes itself? I don't know if I was clear. So could it be a machine that learns how to solve problems as it solves problems? Can it change itself to solve problems in different ways?
That's an interesting question. Yes, there's no reason why the Turing machine shouldn't be programmed to modify its own code. So you could have the Turing machine running a chess playing program, for example, and it might modify its own code in accordance with the way the game goes.
Mm-hmm. Yeah. So in that case, so thinking about yesterday's talk, I don't know if you are familiar, probably you are, with the adversarial neural networks, for example, where it tries to do something and the other network would somehow do something in another way, and one would modify the other so that gradually they improve the performance of each other. Could we model Turing machines in that way? It's a universal machine, so in principle, yes, right?
Well, you could certainly use the universal Turing machine to simulate the two adversarial networks. It could all happen on the tape of the Turing machine. And also, I mean, you could have two Turing machines you know, sort of acting adversarially towards each other, and so learning. So, you know, instead of having adversarial networks, you'd have two adversarial Turing machines.
Mm-hmm. So I'd like to have some questions from the audience here. Paula over there. So can you keep the microphone there, please? So Paula, introduce yourself, please, and then ask your question.
Okay. So good morning. My name is Paula Costa. I'm a professor at the Electrical Engineering and Computer Engineering School at the University of Campinas. So thank you very much for your lecture. My undergraduate graduation course was on electrical engineering. So we learned about computers, talking about a lot about von Neumann, and I never heard about Turing during my undergraduate course. And my question is, what do you think that is the main danger of not preserving the correct history in the computer science on computer science course, right? I mean, I believe that it's very important to know the contribution of the founding fathers, but nowadays it's been really hard to track all the contributions of the main developments on computer science. And what's the danger about that? I mean, as a professor that has the responsibility of teaching the technical aspects of technology, what's the danger of not rescue the history of things, the origin of things, in your opinion?
Yes, thank you for that question. Well, there's the sort of general danger of falsity. I mean, there are two ways in which you know, the history might not be preserved. And one is just that, you know, it's forgotten. You know, it's like the, you know, kind of in the Pleistocene or whatever, you know, we just don't know. And, you know, kind of somehow that's okay. It doesn't really have any practical implications. So if the, you know, if the work of the pioneers was simply forgotten, well, you know, no practical implications, no danger. It's just we don't know, and that's sad, because, you know, the past is so interesting and it's great to know about it. But if for some reason that portion of the past is no longer accessible, well, we can live with that. There's no danger. But then the other case is where truth is replaced by falsity. You know, it's not just that the true story has been lost, it's that it gets replaced by false stories. I think that's the dangerous case. And it's dangerous just in the, you know, all the ways that falsity is dangerous. What do you think, Zhao?
Yes, I totally agree with you, what you have said. And indeed, I mean, if you look at the textbook for computer science or the history of computing, even for nowadays, I mean, there are still like omissions of Turing. So it's quite important, I think, I mean, to have a really a neutral understanding of the history. Otherwise, by, you know, education generation by generation, then as Jack said, I mean, maybe the false story or inaccurate picture would just pass. I mean, and people may never know like the actual history.
Thank you. We have one more question here. Please introduce yourself before asking the question.
Hello, thank you, Jack, for your presentation, for the historical background that you have shown to all of us. We really appreciate. My name, I'm just presenting myself. My name is João Pedro de Mello, and I'm a student of electrical engineering. My question is, according to the speech of Melanie Mitchell yesterday, I would like to know from you if it's possible, for example, train neural networks to develop higher abilities as a one-year child would have, for example, to have spatial capabilities, or even to develop a sense of consciousness as little kids have, not just to learn from empirical data, or if so, how empirical data could be used to train such machines to make such, to have such consciousness about this.
Well, I didn't hear the talk yesterday, so I'm not really familiar with the background. But if your question is just a general one, kind of could a neural network be built so that it had spatial abilities and could behave intelligently? I mean, I'm fairly buoyant about AI. There is no reason to think that's impossible. If you get more specific and say, well, could a neural network made out of these kinds of neurons develop spatial abilities? Well, then that's an empirical matter. I mean, I guess we all know that today's neural networks, they're simplifications to one degree or another. The neurons are, they're not really accurate representations in any way at all of, the much more complex devices we have in our heads. So could a particular neural architecture made out of particular artificial neurons develop spatial ability? It's an empirical question. You also talked about consciousness. Could you train a neural network to become conscious? I very much doubt it. That seems orders of magnitude different from spatial ability and even from intelligence. Could you train a neural network of some description to behave intelligently? Well, why not? Kind of AI is possible. Could you train a neural network of some description to become conscious? I don't, despite my general buoyancy about AI, I don't feel any temptation to kind of say, well, yes, of course, to that question. Consciousness is much trickier.
Can I just make a compliment? I would like to hear the opinion of Robert, if he has something.
Okay, that part, Robert, you can. That's a good point. I was going to say that it's now time to go to Robert Allman's talk. So, Robert, if you wish to start your talk, you can, and if you want to answer Vitor first, you can as well. You can choose. But it's your turn now to start your talk. Thank you very much, Jack and Zhao. Jack, I think it's time for you to go to bed. And Zhao, if you wish to stay, you are welcome. But we should move on to Robert Allman's talk. So, Robert, can you share your screen with us, please?
Yes, I'll try. Okay. Here we go. Okay. Here we go. Okay.
Thank you.
Yeah. Okay. So now, as Professor Copeland ended his session, directly leading into my session, into what we're going to talk about next, and that is consciousness. Okay. We're going to talk about consciousness, and let me, okay. So the question we're going to address is why consciousness, okay? Now, there are three questions in life science: what, how, and why, okay? And what are we discussing, okay? How does it work? What's the mechanism? And why is what purpose does it serve, okay? So let's illustrate this. An example is digestion. What is digestion? It's transforming food to a state the body can use. How does it work? Okay. It's with chewing, stomach, intestines, waste disposal, all kinds of things. We understand the mechanism quite well, the mechanism of digestion. And why? What do we need digestion for? Well, it's to get energy, to grow, to get ingredients for bodily functions. This is what digestion is all about. So now we're going to ask these three questions for consciousness. Okay. Now, Professor
Robert, sorry to disturb you. The slides are not passing. I think you are sharing the office screen, not the slide screen. We are still seeing the first slide.
Okay, you're just seeing this slide. Okay, I don't know what to do. What should I do what do I have to do?
I think you. I'm not sure, but you are not sharing the. So stop the presentation. I stop the slide presentation and keep only the office window.
Stop the sharing. Okay. Now what should I do?
No, open again. But open
again. Share screen. Okay. Share screen. Fine. Okay.
And
here we go. Here we go. All right.
Okay, that's perfect. Now it's perfect. Okay, you did it.
I did it. Now let me go on to the next slide. Wait a minute. Now I am not able to advance the slides like I did before. Wait a minute. Let me call the our computer man. Maybe he can help us. Okay, just a second.
Don't worry.
I'll call him and we'll bring him in here.
So, Oren, just after the questions of Alman's talk, we are going to have a short break here. I'd like to invite you to have a coffee break with us, but it's not possible yet. One day in the future, maybe.
Okay, I'm back. And we have the computer man with us.
Try pressing the space bar.
Try pressing what?
The space bar.
Space bar. Okay. I pressed the space bar.
Doesn't
now.
work. Okay.
Oh,
okay.
Okay. Now we got it.
Okay, perfect. It's working now.
Okay, now do you see the next slide? Three
Yes.
questions in
Everything
life
perfect
science?
now.
Yes?
Yes, perfect.
Okay, good. All right. So let me start again. So we heard about consciousness in the previous slide. Actually, this conference is about artificial intelligence. And we're going to talk about something which is not really in the realm of the conference, because it's real intelligence. It's not artificial, okay? It's real intelligence, and not only intelligence, but more generally consciousness, okay? And Professor Copeland brought it into the conference just at the end of his speech, so we're going to take him up on that. All right. And we're going to address the question of why consciousness. Now, there are three questions in life science, which is what, how, and why. And so what are we discussing? What are we talking about? And in most applications, it is pretty obvious, as we'll see, but not for consciousness, okay? How does it work? What's the mechanism? And why is, what purpose does it serve? Those are the three basic questions in life science. And the example is digestion. What is digestion? It's transforming food to a state the body can use. It's how does it work? Well, all kinds of all kinds of mechanisms that help in making digestion work: chewing, stomach, intestines, waste disposal, and so on. We know how digestion works. And the reason for why we need digestion is we need food to get energy. We need to grow, to get ingredients for bodily functions. We know very well what the evolutionary function of digestion is. So now we're going to ask these three questions: what, how, and why, for consciousness. What is consciousness? Okay. Well, the problems start there, okay? It's not clear what consciousness is. Well, I'm going to suggest this definition. It's the ability to perceive, to experience the outer world, okay? Experience, okay? Not just sense, but experience the outer world. To see, hear, smell, taste, feel heat and cold, okay? Actually, it's not sensing, okay? It's experiencing. Now, it's also the ability to feel, to experience our inner world, our emotions, to desire, to want something, to suffer, love, hate, fear, admire, despise, to get excited, to be glad or sad, to feel pleasure or pain. Those are all functions of consciousness. So that is our inner world, okay? It's not the outer world. The third example, the third element of consciousness is to think and to intend, okay? And the fourth one is to act purposefully, to carry out intentions, okay? To act purposefully, okay? Not just to act, but to act purposefully. To have something in mind when you are acting. That is what consciousness is. Okay. How does it work? Okay. Well, the answer is we simply don't know. Okay, it's the last great enigma of science. We do have some idea of the detailed workings, the neural correlates of consciousness, but we have no idea at all of the big picture. The underlying phenomenon, what the philosopher Chalmers called the hard problem. Okay, we have no idea at all, okay? let me give you an incomplete analogy. Suppose by time machine, a group of astute scientists from the 17th century was delivered into the 21st century, okay? They arrived by time machine in the 21st century, and they were given a computer, a laptop, let's say, okay, to analyze, and they were told, you know, tell us how this works, you know, give us an understanding of how it works. And they would be able, I think, to analyze it quite well, but they would really not understand how it works because they have no idea of electricity. They realize that if you put a wire into two holes in the wall, the thing works, and if you don't put a wire into two holes in the wall, it doesn't work. Well, they have no idea what electricity is all about. So they really don't understand it. They understand the workings of the inner workings of the computer. Maybe they understand, but they don't understand what makes it work. Okay, it's an incomplete analogy, but it gives you some idea. They have, okay. So that is how. We don't really know how it works at all. Okay. We're missing that part. We're missing the hard problem, okay? But we're not going to be able to answer that question today, or tomorrow either. I don't think we're near a solution of that problem. Now, what we're going to address today is why consciousness? What purpose does it serve? What evolutionary advantage does it confer? Why did Mr. Darwin bring us consciousness? Why did he make us conscious? Okay, what's it good for? All right. So the proposal that I'm going to try to sell to you today is that it enables emotions to operate. Okay, not the evolutionary purpose is not in the number one in the previous slide, not the perception, experiencing the outer world, but the basic reason is the emotions, okay? So I claim that emotions are the driving force of human life. We do what we do because we want to do it. And desire is an emotion. And what makes us want to do it? We want to do it because of other emotions. Seeking pleasure, avoiding pain, being afraid, loving, hating, and also these other emotions, we get to them because we are able to experience, because we are able to taste. Yes, we eat food because it tastes good. Okay. So that's also an emotion, but that is also a function of consciousness. Perception is a function of consciousness. Something looks beautiful. We go to a concert because the music is nice, and so on and so forth. Yes. So, wait a minute. Okay. So other than emotions, all the ingredients of consciousness resemble tasks that machines can perform. Machines cannot experience the outer world, but they can and do sense it. Machines cannot think, but that's what this conference is all about, artificial intelligence. They can and do analyze in many ways much more efficiently than humans. Machines cannot act purposefully, but they can and do act. Okay. I'm going to have to call my computer man again because, oops. Hello? Can you hear me?
Yes, perfectly.
Okay. The one thing of which machines are utterly incapable is feeling emotions. Machines cannot desire. They cannot love or hate. Okay? They cannot be glad, sad, pleased, or displeased. It is in enabling emotions to operate that consciousness most clearly displays its uniqueness. As we see here at this meeting, artificial intelligence, AI, is making great strides, but artificial emotions have not gotten off the ground. I don't know, maybe some people tell me that people are thinking about artificial emotions, but as far as I know, there is no significant work on artificial emotions, okay? That is not to say that the other ingredients of consciousness are unimportant. To enjoy tasty food, you must taste it, okay? You have to taste it first. You have to perceive the taste of food, and then you can enjoy it. You can enjoy a beautiful view. You can enjoy seeing your wife or your family or your colleagues, yes? But you have to see them. You have to perceive them, okay? Okay, we now examine the role of emotions in enabling the creation of incentives to meet the three basic needs of human life. And the three basic needs are nourishment, reproduction, and self-preservation. Okay, let's talk about nourishment. Food. Food is required for energy, for growth, and for providing vital ingredients for bodily functions. But people do not eat for that reason. They eat because they are hungry and or because they enjoy food. Hunger is painful. Enjoying food is pleasant. Both constitute incentives to consume food. Okay? So over here, evolution created these incentives using the emotions of pain and pleasure. Hunger is painful, enjoying food is pleasant, and the emotions are necessary for us. I don't know how it is for lower animals or how much lower, yes, but for us, emotions are essential in enabling us to consume food. Next, let's consider reproduction. Okay, that is I think the three essential elements of all life, and specifically human life, but all life, are nourishment, reproduction, and self-preservation. So here we get to the second item, which is reproduction. Sex is required for reproduction. And reproduction is, of course, the driving force of the evolutionary process. But people do not have sex for that reason. They have sex because they enjoy it. Okay? It's pleasant. The pleasure is an incentive to have sex. Evolution created this incentive by using the emotion of pleasure. Okay? Pleasure is an emotion. And that so what enables reproduction in human beings is emotions, pleasure. Okay. Let's go to the third item. The third item is self-preservation. An example of incentives in self-preservation is the phenomenon of pain. Pain calls attention to a problem in the body, something that needs to be fixed. People who cannot feel pain are in deep trouble and usually do not survive long. There are people, there is this phenomenon of being unable to feel pain exists, and such people, you know, it's some kind of genetic mistake, and such people are in deep trouble, and they usually don't survive long because they don't realize when there's something that needs to be fixed in the body. Pain provides an incentive to fix the problem. And evolution created this incentive using the emotion of pain, okay? Feeling pain is an emotion, all right? So let me summarize, okay, my thesis. And the summary is this: the purpose, the evolutionary function of consciousness is to enable the operation of emotions. Now, this is the content of what I wanted to say in this first part of the talk, and this addresses one of the two subjects of this session, and that is the foundations of AI, foundations of artificial intelligence. We're not talking here about artificial intelligence, but we are talking about foundations. And now I'm going to go to the second part, which is the ethical aspects of AI. And the ethical aspect of AI, I don't have very much to say about this. AI, artificial intelligence, is a tool. Like most tools, it can be used for good or evil. So I don't think that the matter of ethical aspects, I don't think there's anything very different about AI as far as ethical aspects are concerned. You can use it for good, you can use it for bad, and there's no special, there's nothing that differentiates artificial intelligence from other tools that you can use for all purposes. Okay? Obrigada. Thank you very much. And that's the end of my presentation, but I have to try to get back. Oh, okay. Here we are. Okay.
So thank you very much. It was a really interesting talk. we have time for questions from the audience. While the microphone goes, so any questions? So a few questions. So starting over there. While the microphone goes there. So Professor Allman, one question: in the scale of evolution, at which point do you believe conscience exists? Let's say we are human beings, we are conscious of ourselves, but the bacteria would not be conscious of itself.
Right.
So in the scale of evolution, at which point do you believe that consciousness exists?
Well, I really don't know. Yes, I really don't know. But this is you know, let me say this. I know that I'm conscious, yes, but I don't know that anybody else is really conscious. Okay. I'm not really sure about that. I experience consciousness in myself, but but perhaps other people are not conscious, but I assume that they are. I mean, that's not that I assume that other people look more or less like me and act like me, and I assume that they are conscious also. So but lower animals, I don't know. I think there is one famous expert in consciousness. I've forgotten his name now. I'm an old man and I'm very forgetful, but he seems to claim that consciousness is in primates, okay, as developed in primates, but not in lower animals. However, I have to say that I don't have a dog myself, but two of my children do have dogs, and these dogs behave as if they're conscious. You know, they really react. They really they seem to feel pleasure. Yeah, emotions. Okay, emotions. Not only perceiving and experiencing the outer world, but also they have an inner world. They seem to display emotions. So I think maybe in certain mammals you have not only primates, you may have emotions, but this is totally conjecture. I don't know. I do feel that fairly certain that human beings are all conscious, but how far this goes down the evolutionary ladder, I don't know.
Thank you very much. We have a question in the audience. Please introduce yourself and ask your question.
Good morning. This is Gabriel. I'm a student here at UFMG. First of all, it's a great honor to speak to you, Robert. I'm a huge fan of your works. So I don't understand much of psychology, but it is commonly said that a depressive person is unable to feel emotion. So with that said, would it be correct to affirm a depressive person somehow loses its consciousness?
Could you repeat the question, please?
A little bit more distant from the microphone, please.
Could the moderator repeat the question so that I can understand it? I just was not able to make out what the question is. Yes, it's not that I don't understand the contents. I simply didn't get the words.
Can you hear me better now?
Yes, go repeat the question, please.
I say that I don't understand much of psychology, but it is commonly said that a depressive person is unable to feel emotions.
What person? I couldn't get that word.
A depressive person.
Depressive person. Ah, okay.
Yeah. With that said, would it be correct to affirm a depressive person somehow loses its consciousness?
Yeah. So, Professor Roman, he said that the depression, it would be a state where the person would be unable to feel emotions. And you claim that emotions are the basis of consciousness. So that's the question. So
in the case of depression, you cannot feel emotions? Is that what's claimed?
Some psychologists say that.
I think if you're depressed, you know, if you're depressed, then I think you can certainly feel emotions. You still want to do something. You can. Depression itself seems to be a form of emotions. You are unhappy about something. Being unhappy is an emotion. Okay. So I don't think that if you're depressed, you can't feel emotions. No, I don't. I think without feeling emotions, you can't exist at all. Human beings, emotions are a requirement for the life of human beings.
So I understood your answer. Thank you very much. It means that a depressive person certainly feels emotions.
Certainly, yes. It's not very pleasant, the emotions that he feels, but he feels emotions, yes.
So next question, please. The microphone is going there. Okay. So, yeah, please.
Hello. Thank you for your great presentation. It's an honor to be here, Professor Alman. I have a question. Would you consider it possible to make it closer to artificial consciousness if we could somehow simulate emotions through reinforcement learning, because it's a method that we give credits to the machine, rewards or penalties? And what if we could somehow simulate emotions, like if the machine is getting happier or sad or angry, something like that? Thank you.
The question is whether one could simulate emotions in a machine. Yes, is that the question?
He said yes, but also he claims that some artificial intelligence training techniques could be used also to simulate emotions.
I think
Something
you could simulate emotions. Okay. You could simulate emotions, but you can't feel the emotions, okay? A machine cannot feel emotions. A machine cannot, and I think that is the basic emotion that is necessary for human life is to want something, okay? To desire it, okay? A machine cannot desire. You can simulate emotions in a machine. You can make the machine act as if it desires something, or as if it's happy, but it's not happy, okay? And it doesn't desire, and desire is needed to make us act. Whatever we do, we want to do it, okay? We want to do it. Okay, there are some things that we do that we don't want to do, that like breathing, okay? Breathing, or some automatic responses of the body. But in most of the things we do, you know, which are not automatic, like breathing or digesting, yes, we do them because we act, because we want to act, and there has to be something that makes us want to act, okay? And you cannot get a machine to want something. You can simulate emotions, maybe. You can make it. So that's why I'm not entirely certain that a dog has emotions, but he certainly looks as if he has emotions. And so you can maybe simulate emotions in a machine, but you can't. It's as if, but it's not really true. A machine cannot want, at least up to now. I don't say this that it's impossible, but up to now, a machine cannot want.
I think he answered your question. So next question, please.
Thank you, Professor, for your lecture. Pleasure to talk with you. My name is Thales. I'm a physician, and I'm also studying philosophy now. You gave us examples of what emotions are, and it's quite intuitive to see that. But I wonder if you have a theory of emotion, because complementing the question of the colleague, I think there are some people that say that emotions are kind of automatic programs to act fast without reasoning, and that would answer your why question. In that sense, I think it would be easier to program emotions. So I'd like to hear more about if you have a theory of emotion, what is this theory? Thank you.
I didn't get the question. Could you
Please repeat it, please? Yeah, again, let's make it simple.
Do you have a theory of emotions? Because you gave us intuitive examples of what emotions are.
You have a theory of emotions? What?
What emotion is for him?
A definition for emotion.
Okay,
but not the definition.
The definition, I gave it on my presentation. It's experiencing our inner world, experiencing what's going on, experiencing our inner worlds. Yeah, that's the best I can do. I think, I think, in fact, you can ask a different question, and that is, what do you mean by the word experience? Okay, so it's not only emotions, but the perception also. Perception. I define perception as experiencing the outer world, okay? Seeing, hearing, tasting, smelling, okay? Feeling hot or cold, experiencing the outer world. Now, that is my definition, that is, experiencing is the definition of consciousness, okay? Now, but what do I mean by experience, okay? How do I define experience? Well, I can't answer that question. Yes, I can't answer that question because that is consciousness. So if you're not conscious, yes, then you don't know what experience is. Okay, then it can't be defined. You know, it's just like trying to explain what it is to hear to a person who is deaf from birth. Yes, he is from birth. He was unable to hear. His hearing is not just impaired, but he has no hearing. He's not able to hear. Now you try to explain to him what it is, what music is. You're not going to be able to do it. Okay. You're not going to be able to explain to a person who is deaf from birth what music is. You can explain to him sound, you can explain to him octaves, maybe you can explain to him the physics, but you cannot explain to him what music is, okay? So I cannot explain what experience is to a person who is not conscious. And I can't explain what emotions are to a person who is not conscious, okay? And I think the best I can do to define it is experiencing our inner worlds. Experiencing what goes on inside of us.
Okay, so thank you also. It's a problem that's not solved yet. So I know that there are more questions here, but I think because of the coffee break, we're going to have only the last question here.
Hello, Professor. Thank you for your talk. In your opinion, if you think simulated feelings or simulated consciousness could make machines more efficient?
What was the question? I didn't get it again. Yes, I mean.
Can you hear me properly?
I didn't get.
Again, so can you repeat the question?
If, in his opinion, things simulating emotions with computers make them more efficient.
You said before that we can simulate emotions, but we cannot make a computer feel emotions, at least not yet. Somehow, would it be useful to have emotions simulated? Would it make a computer more efficient because of that?
I don't think so. No, I think you have to. I think the answer is no. You can simulate what the outer appurtenances of emotions, but you can't. I mean, I think a computer, you cannot get a computer really to want to do something, okay? You can make it appear as if he wants to do something, maybe, yes. But if he doesn't want to do it, then you're not going to be able to. This is not the. If you simulate desire, that's not like desiring. Okay, it's not the same thing. You can the outer aspect of desire maybe can be. You can make it appear as if he desires, but he doesn't really desire. And what makes emotions not only useful, but you have to have them. Human beings have to have emotion. What makes them an essential part of human life is that you actually experience the emotion inside. You actually want to do something. You have to make people. You have to make the computer want, and I don't think a computer can want.
So thank you a lot. There are more questions here. I will ask people to send me the questions, but we are now 15 minutes behind schedule, so we should move to the coffee break. Professor Allman and Oren, I'm going to be here in solidarity to you because you cannot have the coffee break with us. But we should come back in 15 minutes. So all of you who want to, you can leave now for the coffee break. Professor Allman, thank you a lot for the talk.
Okay, thank you.
Obrigado, professor Reni Herria. 20 minutos, então, para o café, será servido aqui no saguão.
15 minutes. 15 minutos. So, Oren, you are going to be...
Sim, 15 minutos, retornaremos, então, com fundamentos e aspectos éticos da inteligência artificial e ciências cognitivas. Lembrando para vocês também que o conteúdo das palestras ficará disponível na plataforma durante 30 dias. E quanto aos certificados, serão enviados para o e-mail que vocês usaram para a sua inscrição, tá bom? Voltamos, então, em 15 minutos. Obrigado. Hoje, às 17h30, nós teremos uma atividade extraoficial do nosso patrocinador, a Vetor Editora, com a palestra Uso e Benefício da Tecnologia na Avaliação Psicológica, com Vanessa Paixão, representante da Vetor Editora, será hoje às 17h30. Vamos dar sequência, então, continuando com fundamentos e aspectos éticos da inteligência artificial e ciências cognitivas. Eu passo a palavra ao professor Reni Herria.
It's now time to continue. So, Oren, you are the last one. In my opinion, it's a good thing because now you know what the others already spoken, and you have a chance to give your talk knowing what already happened. We continue our meeting today with Professor Oren Chagri. He's a philosopher and Schumann Chair of Philosophy and Cognitive Science at the Hebrew University of Jerusalem. It's a pleasure to have you here, or not here, but here somehow. You can start your talk if you wish. People are coming. I will. So let's wait 1 minute. So a talk sometimes lasts a little more than expected, but a coffee break always lasts more than expected. Okay, I think we can start. So, Professor Orachagri, the time is yours now.
Thank you, and thank you for inviting me. This work is joined with Dr. Lotem Elber de Rosgo, who did her PhD at the Brain Science Center at the Hebrew University. Now she's doing her postdoc at Pittsburgh University. And my talk is more at the foundations of cognitive science. And specifically, I will discuss the more general question is about the relations between computational and mechanistic explanations in cognitive and neuroscience. So computational explanations are explanations that refer more to the mathematical details and operations of the nervous system, and mechanistic explanations are taken to refer more to the biological, physical, and chemical details of the nervous system. And there is a big question how the two kinds of explanations play together in cognitive and neural theory. We focus here on more specific question, and this is how the computational explanations integrate within what is called the hierarchy of mechanistic explanation. And more specifically, the issue is this. On the one hand, you see on the left side, computational the relation of implementational from the more computational or formal operations like big P and big Q to physical states and properties, here small p and small q, this implementation relation here in the green dashed arrow is taken to be one-to-one, even some homomorphism relation. So each computational state is mapped to some physical state. On the other hand, at least according to what is known as the mechanistic framework in philosophy of science, mechanistic explanations are hierarchical and decompositional. And this means that if you want to explain a certain phenomenon, you have to decompose it to its components, to its part, their activities, the function, and the relation between them. And furthermore, you can further explain each such activity by decomposing it into its components, activities, and relations between them. So the question, if this is the picture, then it looks like the computational operations cannot be constituted or mechanistically constituted by its implementational details, because the implementational details are not parts of them, because we have some disparity between the one-to-one relation and the part-whole relation. So this is the issue, and my talk will have basically two parts. In the first part, I will elaborate on this problem, and then in the second part, I will discuss possible solutions. So first, about the problem. So it is very common, especially in neuroscience, to see the world as coming in some levels. And within the framework of levels, one very popular one is the level of organizations. So that, for instance, the whole brain is divided into levels. And like in this picture from the famous book of Churchill and Seniowski, The Computational Brain, And the idea is, in the level of organization, one of the ideas is that the entities at each levels are part of an entity at a higher level. So for instance, if we have networks, so the neurons are basically parts that constitute the networks. Each neuron is part of the neurons. Basically, the networks consist of the neurons. The mechanistic framework in philosophy of science accepts this picture, and they say in addition that each such level is a mechanistic level. And what it means, so when we talk about mechanistic explanations, they have several aspects. One is that they are causal. First, they explain some phenomena, they aim at some phenomenon by describing their underlying causal mechanism. The second aspect is that these explanations are decompositional. And what this means, it means that we explain the phenomena in terms of its components, their organization, and their activities or functions. So, and the third part is that the full picture of explanation is hierarchical. And this means that each component in an explanation can itself be further explained mechanistically. So for instance, in this very famous picture from Carl Craver's book from 2007, if we want to explain how the ability of the mouse to navigate, so we can do this by decomposing this ability into its components that are basically the cells in this picture. In the hippocampus, we can think about the place cells and the grid cells, their activities and their interactions with them. We can simply explain the navigation if we look at the what is called the spatial map that is constituted by the cells, the relations, and their activities. And furthermore, if we want to explain how each place cell is performed, we can further analyze it, decompose it, and explain it in terms of long-term potentiation, and so on. So this is basically the mechanistic picture. And the important thing is that each level here fully explains the a certain phenomenon, and each level includes exactly those aspects that are causally relevant to the constitution of the phenomenon. Okay, so so this is about mechanistic explanation. Computational explanations in cognitive science and neuroscience first provide mathematical descriptions of the nervous system. In this sense, perhaps they are not very different from explanations, some explanations in physics that are also mathematical descriptions. But at least in neuroscience, the assumption is that the brain itself computes. And this means that the brain itself, the explanations themselves refer to some mathematical aspects in the brain, or formal or abstract aspects, what philosophers like to call sometimes medium-independent properties. And this means that they do not require a specific physical medium. They can be realized even not just in nervous systems, but also in artificial systems. This is part of the promise of artificial intelligence, that basically if you mimic the computational properties of the brain into some another system, artificial system that is not biological at all, this system can be also intelligent. Of course, there is a debate within the philosophy whether these abstract properties are sufficient for being computational, but I will put it aside. And I refer to computational properties as abstract, mathematical, formal, or medium independent properties. And as mentioned before, the assumption is that these more computational formal states and operations are implemented in some neural states, so in the brain, and that this implementation relation is some morphism one-to-one mapping. So in this respect, in this picture, yes, so we can map the weights here to some synaptic activity or changes in the cell, and so on. And more generally, the picture here is is provided by the famous paper by David Chalmers, who provides a theory of implementation, is that we basically the implementation relation is one-to-one mapping relation, in which if we want to mimic the formal relation if P then Q, then the implementation is we have to map the formal state big P into the to map it to a small to a physical state small p, big Q to small q, and the causal relation between small p and small q, the physical relation, mimic or reflects the formal relation between P and Q. Yeah, and this idea that of implementation, and this that is a one-to-one relation, we find it often in neuroscience. So in this paper by Botvinnik, Niv, and Barto, they provide a model of learning, of reinforcement learning. Here on the left side is the more mathematical model, in which it consists of an actor that basically selects the action based on a policy that is based on action strength, and there is a critique that maintains and updates the in this case the state values, and the idea is that both the action strength and the state values are modified, and they are modified based on some feedback from the environment. And the key element is the reward prediction error, that we can think of it as the difference between the reward received from the environment given a certain action and the previous value. So if the difference is positive, then probably we will give more strength to this state value and to the action strength. And if the difference is negative, the other way around. But the authors also provide what they call neural correlation picture. And in this neural correlation picture, you can see basically the elements that implement each of these operations. And as you can see, the assumption here is that this relation is one-to-one. So for instance, the reward prediction error is mapped into levels of dopamine, and so. So the question, given all this, is really how do the computational states and properties integrate with the implementational properties within the hierarchy of mechanistic explanations? So to make it more precise, there are several premises here. The first premise is that computational explanations describe some abstract operations in the brain. The second premise is that these computational operations are implemented in some neural states, and that this implementation relation is one-to-one mapping relation. And the third premise is that the implementational states are often part of a mechanistic hierarchy in which the relations are that of part whole in this case. So the question is how exactly we fit these computational operations we see in the mechanistic hierarchy. We cannot simply squeeze them in because these relations are one-to-one, but the relations between within the mechanistic hierarchy are that of part whole. So it seems as if the computational operations are left out. So this is really the puzzle that we want to present in our paper, and then we offer several solutions, and we let each one of you choose the preferred solution. So these are the possible solutions. So first of all, we can the whole problem emerged from three premises. So one can deny one or more premises. So the first premise was that computational explanations refer to some mathematical properties in the brain, but someone can say, no, computational explanations are simply descriptions. They do not really refer to anything mathematical in the brain, perhaps to something physical. We can take a more instrumentalist point of view with respect to computational explanation, which is one option. Another premise was that the implementational relations are one-to-one homomorphic mappings relations. So someone can deny this. And finally, one can deny the premise that the mechanistic explanation in neuroscience are really captured by the within the mechanistic framework of in the philosophy of science. Maybe mechanistic explanation in neuroscience are not decompositional. Maybe there are no levels, no hierarchy. So all this is possible. We want to see what our options are if we assume that still all the premises are true. Okay, so and here we want to present two different pictures. The first picture, which we call the one hierarchy picture, is to say, really, if you want to explain some cognitive ability, for instance, reinforcement learning, how an action is chosen in the long run, etc., then it is not enough to look just at the mathematical details. You have also to look at the implementational details. So the implementational details are essential for the explanation of, for instance, of reinforcement learning. So really, we don't have here. We have really one level here, one level. So within the mechanistic hierarchy, basically, if we look at this picture, for instance, so the neural and the mathematical details are just in the same hierarchy. So this is one option. This picture, of course, fits quite well with the view that computational explanations are not really full-fledged explanation. They are only what some people call sketches of mechanism. What is a sketch of a mechanism? A sketch is just a description in which some relevant structural or implementational aspects of the mechanism are omitted. Once the missing aspects are filling in this case, the implementational details, only then the description turns into a full-blown mechanistic explanation. The sketches themselves can be thus seen as elliptical or incomplete mechanistic explanations. They are, in a way, a guide or a first step towards the structural components that constitute the full-blown mechanistic explanation. This is from the paper by Piccinini and Craven. So if we go back to this picture, what it means is that just the mathematical description here, the mathematical model is not enough to explain let's say, reinforcement learning, we must also refer to the implementational details. The problem with this solution is, of course, that at least many computationalists think that their models are just fine. They are full-fledged explanation of the cognitive phenomenon, and we don't need really the implementational details. Another comment is that we can, there are two ways to understand this solution. On one understanding is that really all mathematical details are in a way redundant. They are placeholders. Once we replace them, once we find the implementational details, we can simply throw them away. So what is really important is just the implementational picture. Another option is to say, no, we want to have them together. Both the mathematical details and the implementational details are important. And then within the level, we have this implementation relation, which is something which is a bit weird because this is itself is not what we take to be a causal relation. So this is one option. Another option is to say, no, it's like what we call the two hierarchy solution. Here, the idea is this, that each model here simply provides an explanation of a different aspect of it or a different phenomenon, but each model is a full-fledged model. So for instance, this reinforcement, this mathematical model provides a full-fledged explanation of reinforcement learning. We don't really need the implementational details. The implementational details maybe explain something else about the brain. So we basically separate the computational and the mechanistic, and within neuroscience, these are like two explanations that aim at different targets. This picture fits quite nicely with the functionalist view of computation, according to which computational, so maybe people who praise this or advance this view were philosophers like Robert Cummins and Jerry Fodor. So according to it, computational explanations are themselves decompositional and sometimes hierarchical, but the important point here is that they are separated from the more mechanistic explanations, and they are even autonomous in that they need not refer to their implementations, because basically they could be realized, that we said before, in very different physical structures. So this is a second option. The disadvantage of this option is that we still see today in cognitive neuroscience, and this paper shows it, people want to at least make the relation or mention both computational and implementational relations. Yes, so there is some delicate interplay between the more mathematical and implementational details, and we don't want to ignore and to say these are not relevant. The only thing that is relevant, as the functionalist will say, is just the mathematical computational details. So a third option that comes under the heading of the mechanistic view of a computation, I will not get into this, is that actually the computational itself consists of two different kinds of explanation. One is more functional, as we just say, what and how the mathematical function in the brain is being computed. And another one is that it's another explanation, is how those mathematical properties are implemented. This, I think, is a quite reasonable solution. The problem with this is that the implementation and explanations itself is not mechanistic in the sense of part whole, is not decompositional, because it just shows the one-to-one mapping relation. So basically we have one explanation which on the left side, and a second explanation which shows how each mathematical operation is implemented in the brain, and this relation is one-to-one, so it seems that the mechanistic hierarchy is in a way completely redundant. So so basically this, so I'll let you choose the preferred solution. And so this is just the summary. We raised the problem of how computational explanations integrated into the mechanistic hierarchy. And at the end, consider two possible pictures. On the one hierarchy picture, computational and implementational properties reside in the same level of explanation. And this picture fits nicely with the view that computational explanations are sketches of mechanism. Disadvantage that they are not full-fledged mechanism explanation. And on the two hierarchy picture, computation and implementational properties reside in different hierarchies or different explanation. And this view fits nicely with the functional view, according which computational explanations are separate and autonomous from mechanistic explanation. We can try to somehow integrate both and to say that the computational theory needs both the functional and the implementational, but it is less clear how it fits with the mechanistic part-whole hierarchy. So basically, that's it. And thank you. Thank you for listening.
Thank you a lot. We have time for questions. So any questions from the audience? Well, the microphones are here. So before we go to the audience, so Oren, one question. This computational model for the neuron has a lot of applications nowadays. Use it a lot in many applications.
Right.
After in your slide that shows the comparison between biological and computational neuron, where just a moment, is a nice model, and all the analogies that you made are clear. The question is, do you believe that we need more complex model, both from the biological point of view or the computational point of view, to really achieve this mechanist hierarchical analogy between biological systems and computational systems? Do we need more complex models for the neuron?
Yes. So my personal view is that yeah, we somehow have to figure out how they are integrated together. Yes, and I think that probably, yeah, at the end of the day, surely we will need more complex computational model and more complex biological model. And I think it is also agreed today that at least in order to discover, you know, the computational details and the biological details, it is a good idea to look at both, because they inform each other. What I think is still puzzling is how the two, whether let's say the two models, let's call them, the biological and the computational, whether they, as I said, whether they form completely different explanations, or, you know, somehow we have to integrate them together. And yeah, I'm not sure what is the answer.
Me neither. Because I live, so I'm an electronic engineer, so I come from the part of electronics and computer science. And gradually I started to somehow to collaborate with people working with neuroscience and working with biological inspired models for those things. And all the time I have these things competing in my brain, trying to figure out to which extent should we simplify things in order to make them tractable, and to which extent we have to make them more complex in order to make them realistic. And that's why I asked this question for you. Do we have more questions from the audience? So the audience, I think the audience is now trying to understand what you said, because I cannot see. Yeah, one of the persons here said that we are trying to digest what you said, because they are trying to understand. Yeah. Do we have questions from? Yeah, we have. Okay, did you send to me? So we have in the WhatsApp, we have questions. Let me see if I can hear. Where is it? Do you have it? Bring it to me, please. Michael. I've seen your. Okay. Okay. This is from before, right?
Yes.
Okay. So we have questions written here. I have to see to whom they were asked. So we have now. So thank you a lot, Oren and Robert. Now the questions that I have here are for all of you. So I will ask them, and you can choose which one is going to answer it. The first question here is, if the human being can learn with models, why a machine can't learn with a model of feelings? That's, I think, for Robert Altman. So I will repeat, Professor Allman, I repeat the question. If the human being can learn with models, why a machine can't learn with a model of feelings? I think it can learn, but one thing is to learn, the other thing is to feel. But if I understood well your talk. Professor Allman, can you hear me? I think not.
Could you repeat the question, please?
Yes. The question is very objective, but I think not so easy to answer if I understood well your talk. If the human being can learn with models, why a machine can't learn with a model of feelings?
With a model of what?
Feelings.
Feelings.
Yeah.
A human being, a machine can learn. Yeah, we know that there are very good learning algorithms for machines. Yes, a machine can learn, but a machine can't have feelings. Okay, I don't understand how a machine can have feelings, can desire. Okay, I don't understand how a machine can desire. So it could learn things, but it cannot desire. Okay, what do you mean? Are you asking whether it can learn to desire? No, it can't learn to desire. Yes, it can learn how to play chess. Yes, it can learn how to play Go. It can learn how to recognize pictures. But somebody has to tell it, we want to recognize the picture. Yes, the machine can't want to recognize the picture. We have to tell it what to learn. Yes, okay, that's my answer.
Yeah. And I understand it. One thing that let me speak something now. 5 years ago, I was teaching for fresh students, so the first year students in our School of Engineering, and I decided to give them a paper that a journal called Physics Today published 5 years ago about what could be published in science or physics within a century. And one of the
What
papers
can
that
be published in physics when?
so in the future, a century in 2116. So within a century. And one of the papers that they put there would be the emergence of consciousness in machines. And they try to give an explanation of they don't show how we would get there, but they somehow can imagine that in the future there would be a machine that somehow is conscious of its existence, and the machine itself collaborates with scientists in order to help the scientists to understand what's happening inside it. So it skips the step that we are trying to discuss here of how consciousness would emerge in the machine. The point that I'm trying to make here is that we don't know how, as you said, we can make a machine behave as if it has feelings, but it doesn't have a desire. It doesn't have the feeling in itself. One thing is to model the feeling, while the other thing is the feeling itself. And that's the thing that is somehow puzzling people here. They are trying to skip a step that we don't know yet how to reach. The next question here is I'm trying to a physics student called Daniel, and he, again, in the issue of consciousness, I think this is the issue that is puzzling people here. Could you say if there is a consensus on some kind of characteristic or threshold that we can use in the animal kingdom in order to say this animal has consciousness or doesn't? I think that's the question that I asked you, and you answered me that primates would have consciousness, possibly a dog. If I remember well, you said that your sons have dogs, and somehow they say that it would have. But
Yeah,
go ahead, please.
I think it's really difficult to tell. It's really difficult to measure whether, you know, I assume that you are conscious, okay? That's also an assumption, but it's because you're similar to me and I'm conscious. You look similar to me all together, and we communicate. We look, but animals are different, and I think we can't really communicate with animals, and I really don't know how to address that problem. Yes, I think it's quite possible that you know, you could in theory program an animal, program a computer to act like an animal, yes, or even to act like a human being. Yes, you could program it to act like a human being in theory. I think that the human beings don't work like computers. They do need emotions, and emotions are not but you could in theory program a machine to look like a computer. Yes, to act like you could program a computer to act like a human being. So I think with human beings, it's I think we can assume that they are conscious. Each one, you can assume that I'm conscious, okay? It's a good assumption. But with animals, I'm not sure. You know, even primates, I'm not sure. Not sure. I can't see how to measure that kind of thing.
Yeah, that it reminds me the Alan Turing's imitation game. In the sense that even if we have a machine that can behave like an animal or like a human, it doesn't mean that the machine is is something like that. It
Yeah,
may have
right,
but
yes.
inside it's not. One more question from a student of psychology called Rose. She asked me if you are aware, or Professor Oman, Professor Shakir, if you are aware of artificial emotions, studies about artificial emotions.
There is work on that. There is work on artificial emotion.
Studies about artificial emotions.
Is there? I'm not aware of any work on artificial emotions, but maybe the questioner knows about some work. Yes, I'm not aware of any work on that. I won't say there is no work because I'm not. I didn't study the literature that well, but I'm not aware of any work.
Or are you aware of anything about that, artificial emotions?
Yeah, well, I'm not. I don't know if there are certainly attempts to create, creatures that at least look like as expressing emotions. That's for sure. So there are like, I forgot the name of those sorts of robots that basically we can talk about even pet robots, right? That are sold for created for children, and they in a way the aim here is at least to imitate emotions. Yeah. I don't know if it's really an attempt to create emotion, but at least emotional behavior. So in this respect, I think what you said before, that there is a difference between the behavior itself. So maybe, machines can pass the Turing test. They can imitate the behavior of humans. This is one thing. And another thing is the internal process itself, what's going on inside the organism or the machine. So if most people today, I think, are not behaviorists anymore, and they think that it's not just the behavior that matters, but also the internal process itself. And then there is the question, what is important about the internal process? So some people will say the computational structure, but I see that Professor Uman thinks that this is certainly not sufficient, the computational part. You need something else.
Yeah, today we have
to have consciousness. Yes.
Yeah, today we have computers with huge amount of memories, huge amounts of memory, huge processing capacities, and still they are far away from anything that we could call artificial intelligence as we understand intelligence for ourselves, as far as I can see. So it's not just an amount of memory or complexity. It's more than that. We need some knowledge that my feeling is that after all the discussion we had here, we still need something that we don't have yet. And I don't know exactly what it is. So we are now reaching the end of this meeting, and I would leave the word free for Professor Oran Shagrir and Professor Robert Uman to raise questions or make final comments if you wish.
Yeah, I can just say again, thank you. Thank you for inviting me. Hope that the session was interesting, and enjoy the rest of the conference.
Okay, Vito, yes. I agree with Professor Shakir, and I'm very pleased to be here virtually in Belo Horizonte. And I think this technology is extraordinary. Yes, that you can be. As I told my wife, she said, "Well, what's happening today?" So I said, "I'm going to Brazil." He said, you better leave. It's going to take you. So I said, no. I'll get to Brazil in 3 minutes. Yes. Yeah. Okay. So thank you very much, and for inviting me, and for hosting me. And I enjoyed Brazil. Obrigada.
Thank you. So one question for you. Have you ever been to Brazil? Oren and Robert? Oren, have you been here to Brazil?
Yes, I've been in Brazil twice. Yeah. Last time it was just in November, I think 2019, just before the pandemic. Yeah. And it was great. Yeah.
Where did you go, if I can ask you?
I visited several universities in São Paulo. Yeah, the University of São Paulo and some other universities. Yeah, so I spent a week in Brazil. It was fun. Great country, great people, great food.
Yeah. Well, I've been in Brazil about half a dozen times. Yes, I lost count. I've been in Rio and in São Paulo and in the what's the name of those falls on the border with Argentina? What's the name?
Buenos Aires?
Iguazu.
Yeah, Iguazu, that's right. And I've been in Iguazu, and I've been in the Pantanal. And I've been in many places, also in the you know, where the Amazon splits into two rivers. Yeah, all those. Yeah, I know. I've been all over. So yeah, it's a nice country, and you know, we were talking about incentives during my talk. And incentives is really what makes human beings work. Yes? And a nice example of incentives is in the Pantanal, where the farmers in the Pantanal were shooting the tigers because the tigers ate the cattle. Yeah. And the farmers were shooting the tigers, and that, of course, is exactly the opposite of what we want in the Pantanal. We want to preserve the environment. We want to preserve biodiversity. So that's exactly the opposite of what we want. So they changed all that by saying that if a tiger eats your cattle, then you just bring the carcass, you bring the dead body or the remains of what the tiger didn't eat. Not tiger, leopard. There are no tigers in the Pantanal. I'm sorry. There are no tigers in the Pantanal, but there are leopards, okay? And so you bring the carcass to the officials, and you get a little more than the animal was worth. Yes. So they changed the incentive entirely. So instead of wanting less tigers, they want more tigers. So as not tigers, leopards. Instead of wanting less leopards, they want more leopards. That's the importance of incentives. Yes, okay. And incentives. I come from economics. Okay, that's the way I make a living, and economics is based on incentives. That is the basic word in economics, and I think it's also the basic word in human life, in consciousness, and also in the Pantanal. Okay, so thank you very much.
Yeah, thank you very much. I remember. So just after you said that. I remember now that I read an interview of Carl Sagan in 1992 or something like that, where the first question from the interviewer was, is there intelligent life in Earth? And that he said it's a nice question, because in principle we would say yes, but when we see the global behavior of the human being, it's hard to say that we are intelligent. But we will get there. If we survive, we will get there. Oren and Robert, please, so thank you very much. I would invite you for lunch if you were here. I expect you to be here one day. Oren, if you come to Belo Horizonte, be welcome, Professor Allman too. And I hope to see you in another time in the near future. Thank you very much.
Thank you.
Well, I think we can end the meeting now. We are just in time. Perfect. Thank you very much. Bye. Good night.
Bye.
Good evening.